Well, students, in this lecture, we will study the Taylor's theorem. As I told you earlier, you must have already studied this theorem in your real analysis or calculus course, but still it is worth spending time on discussing Taylor's theorem once again from the numerical analysis point of view. Let us start our discussion with Taylor polynomial for a given function. Assume that we are given a function f, which is n times continuously differentiable at a point, say a, then the Taylor polynomial of degree n for the function f at the point a is given by this expression. Generally, it is denoted by Tn, which is given by f of a, that is the constant term, plus f dash of a into x minus a plus f double dash of a by 2 factorial into x minus a square, plus it goes on till the nth term fn of a by n factorial into x minus a to the power of n, right? So you can clearly see that since a is fixed, this is a polynomial of degree n, and that is called the Taylor polynomial of degree n. Since we need the nth derivative of the function f, we generally assume that f is n times differentiable if we want to write the Taylor polynomial of the function f of degree n. So once you are given a function f which is n times differentiable at a point a, you can always write the Taylor polynomial of that function f at that point, which is given by this. Let us now take an example and see how this Taylor polynomial compares with the original function. In our example, we will take our function f to be e to the power of x, and when you take n is equal to 0, you can see that t0 of x is equal to e to the power of 0, which is 1, right? So that is what is given here, and I'm representing that constant in this graph by the red line, and the blue line is the graph of the function e to the power of x. Okay, you can see that only at the point x equal to 0, your function value f of 0 coincides with the Taylor polynomial value, which is nothing but the constant 1, right? Let us take n equal to 1 and see what happens. When n is equal to 1, recall your Taylor polynomial is f of 0 plus f dash of 0 by 1 factorial into x minus a we have taken as 0 here, to the power of 1, that is nothing but 1 plus x, because we have taken f to be e power x, right? This is the Taylor polynomial of the function e power x of degree 1, and it is shown in this graph by the red line. When we take n is equal to 1, we can roughly see that graph of the Taylor polynomial more or less coincides, not exactly, but approximately coincides well with the function value in a small neighborhood of 0. Unlike in the previous case, it coincides only at the point x equal to 0, whereas here, at least visually, we can see that it is approximating very well the function f of x equal to e power x in a small neighborhood of 0. Let us take n equal to 2 and see what happens. In the case of n equal to 2, we have the Taylor polynomial of degree 2 for the function f of x equal to e power x is given by 1 plus x square by 2. Its graph is again shown in the red solid line, and the graph of the function e power x is shown in the solid line blue. So here you can see that the Taylor polynomial of degree 2 is approximating the original function e power x in a little bigger interval than it was approximating well in the case of Taylor polynomial of degree 1 in the previous slide, right? We cannot say that it is exactly equal, but it is well approximating. That is, the Taylor polynomial is well approximating the original function f of x equal to e power x in a little bigger neighborhood of the point A equal to 0. That is what we are understanding through this example. Let's go to the Taylor polynomial of degree 3, and you can see that as expected, the approximation is good in a much bigger interval here, and it goes on like this. When you keep on increasing the degree of the polynomial, the Taylor polynomial approximates the original function in a bigger and bigger interval. That's what we are inferring from this example. In the case of fourth degree polynomial, you can see that from in the interval -1 to 1, your function f is approximated well by the Taylor polynomial of degree 4. And when you go on increasing the degree, this story goes on, and you will see that the Taylor polynomial of degree higher and higher approximates the function f of x equal to e power x in a larger and larger interval. Now the question is it always true for any function f? Well, we have taken here a very nice smooth function f of x equal to e power x. Therefore, we could see that we can write Taylor polynomial of any degree, right? But if you are working with a function which is not a smooth function, then there will be a problem in even writing the Taylor polynomial beyond certain degree. And also it is a question whether this polynomial approximates the original function well or not. Okay. Now I hope you understood what I meant by saying approximating. Okay. So we will come to the precise definition little later. Now just intuitively understand what I meant by saying that the Taylor polynomial is approximating the function. Okay. That is, we can say that f of x is approximately equal to t4 of x in the interval -1 to 1 in this particular case. That is, in the case when f of x equal to e power x. This much we can say. So based on this idea, let us try to state the Taylor's theorem. Assume that the function f is n+1 times continuously differentiable. What it means, I can find f dash, f double dash, and so on up to fn+1 time. And the function fn+1 is also continuous. In fact, in this case, all these functions are also continuous functions, right? So we assume that f is n+1 times continuously differentiable on an open interval containing the point A. The point A is the point around which we would like to approximate the function f by the Taylor polynomial. So once you are given this much, we of course know that we can approximately write fx by, in fact, n+1 of x we can write, but for some reason we will only restrict to tn, and you will see that the higher degree term will be written as a reminder. So the theorem says then there exists a number c between the point A and x such that you can write f of x. Remember, if you take only this much, you can only say that f of x is approximately equal to. We have seen in the last example that the function f of x will not exactly coincide with the polynomial for all x, but it can approximately be equal to the polynomial in a small neighborhood of a. That is what we have seen in the last example. So if you just take only tn of x, you can only say that f of x is approximately equal to, but then what you are missing, okay, that is when I want to work with Tn of x instead of f of x, what is that I will be missing? Okay, that missing term is precisely given by this expression. Unfortunately, it is not fully a known quantity, even though we know f, and we know that up to n plus 1th derivative we can find from f, but still this expression is not fully known to us because this c is something which we do not know. Okay, the theorem only says that there exists a c. It doesn't tell you what precisely that c is. If you go through the proof of the theorem, you will come to know that we cannot construct such a c, but we can only see the existence of such a number. Therefore, this term is actually unknown. Nevertheless, we can give an expression mathematically for what we are losing in this approximation, right? Therefore, the theorem says that f of x is precisely equal to, so this is what is important here, precisely equal to the polynomial plus this term. Later we will see that this is called the truncation error. Okay, so here we know that Tn is a Taylor polynomial of degree n of f at the point A, and the second term, which we later call as truncation error, is commonly called as the remainder term. This is the Taylor's theorem. The advantage of this theorem is that if you are given any sufficiently smooth function, you can write it approximately by a polynomial. This formula is also called the Taylor's formula for the function f about the point A. So these are the two things. You are given a function f and a point A. You are approximately writing that function f in a small neighborhood of A in the form of a polynomial. That is what precisely the Taylor's theorem says. In the process of writing the function f approximately as a polynomial, what you are missing is this remainder term. From the numerical analysis point of view, we will call this remainder term as truncation error. Let us take an example. Let us consider the same function as we have considered previously, f of x equal to e power x. And as we have done in the previous slides, we will take a to be equal to 0, just for an example. Then you can apply this remainder term formula and write precisely what the expression for the remainder when I take n is equal to 4. Remember, the remainder term or n is going to involve n plus 1th derivative. So one derivative more, and that is evaluated not at a. Remember, it is not evaluated at a. That is the whole problem of this Taylor expansion. It is evaluated at some unknown term. Just imagine if this was a, it means you can write any function as a polynomial, and what you are missing, that remainder is fully known to you, right? So that is too much to expect. Okay, therefore the remainder should remain unknown to us, right? So that is why you have that unknown quantity sitting here and make our entire life complicated because of this. N plus 1 factorial into x minus a to the power of n plus 1. So you just substitute e power x for f. N is equal to, say, 4. Therefore, you have 5th derivative of e power x evaluated at some unknown point c. That comes to be e power c divided by n plus 1 factorial, that is 5 factorial. A we have taken as 0, therefore it is x to the power of 5. So this is your remainder term. What is c? C is any point between x and 0. X is the point at which we are interested in approximating the function f by the Taylor polynomial. It is very near to 0, x is, and C will lie between x and 0. So suppose you are interested in approximating the function f of x in a small neighborhood of 0, then the C may lie anywhere. We don't know where it will be lying. Anywhere in a small neighborhood of 0. Suppose you want to approximate your function at the point x, it can lie anywhere between x and 0. That is what the theorem says. So in this case, the remainder therefore is written like this. So therefore, your function e power x can be approximately equal to the Taylor polynomial in a small neighborhood of x, but if you add the remainder term also, then it becomes exactly equal to, right? So in this case, the Taylor polynomial is given by 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus x4 by 4 factorial. So that is your Taylor polynomial of degree 4, and the remainder term is given by this. Okay, so if you have only this much, then you should not forget to write approximately equal to. In numerical analysis, you should be very clear about when you have to use approximately equal to and when you can use equal to. Suppose if you write e power x is equal to t4 of x, say for instance, this is a wrong statement. Okay, in numerical analysis, we cannot accept this statement. Okay, you have to write carefully that e power x is only approximately equal to. This discipline should be followed everywhere in the course, not only in the context of Taylor representation. It should also be followed in any method where you are representing something approximately. You should always remember to use the notation approximately equal to instead of exactly equal. Here it is exactly equal to because you have also included the remainder term. The theorem says then e power x is exactly represented by the polynomial plus some unknown function. Okay, why this is unknown quantity? Because C is unknown. Let's take a numerical value for x and see how this representation looks like. In particular, let us take x equal to 1. Then we know what is the value of E. Value of E is given by 2.7183. Why again I put approximately equal to? Note, I have only written approximately equal to because this will keep on extending to many digits, but I have just stopped up to 4 decimal points. That is why I put approximately equal to. Again, I'm telling, in numerical analysis, we will take such notations very seriously. If you put this is equal to, I will simply not accept this representation. And you can just plug in x equal to 1 in this expression, and you can find the Taylor polynomial of degree 4, and its numerical value is something which can approximately written as 2.7083. Why approximately? Because it may be having more digits, but I have only represented it up to 4 decimal digits. That is why I have used the notation approximately equal to. So since we have the numerical values explicitly, we can clearly see what you are going to lose if you use T4 of 1 instead of E in your calculations, right? So it is nothing but the difference between these two numbers. Therefore, E minus T4 of 1 is again approximately equal to 0.01. Now, you can also try to estimate the remainder term. Remember, you cannot exactly find the remainder term because of this unknown term C here. Nevertheless, we can estimate the remainder term. What I meant by estimating the remainder term, let us try to understand it very carefully because this word is used very frequently in our course. You have R5, that is the remainder term for the Taylor representation of e power x up to degree 4 is given like this. That is given by this expression. Therefore, I am just putting it here. Now we don't know what is C, but we know that C lies between 0 and X, right? And what is X here? X we have taken as 1. Therefore, we know that C lies between 0 and 1. And E is a increasing function. Therefore, I can simply put the maximum value that C can take, that is 1 here. Okay. So one may just include equal to here, that's not a problem. Therefore, you have e to the power of C can be less than or equal to E, and similarly, X value is 1, therefore that is going to come as 1 to the power of 5 here, and therefore you have this value. E you know is given by this, therefore you can explicitly find the value of this expression. That is nothing but the upper bound of this R5. Remember, we don't know what is R5. It's something which is sitting in a black box. We do not know it, but whatever may be the value of it, its worst value is 0.0227. That is what this remainder term estimate. So this is called the estimate. This upper bound, which is a number independent of C, is called the estimate of the remainder term. It says that whatever may be this number R5, it cannot take the value something more than 0.225. That's all it says. It means what? The error involved in this representation of the number E by its corresponding Taylor polynomial value is whatever it is, it cannot be more than 0.0227. That is what this analysis says, right? But in this particular example, we have the explicit value of this error. Therefore, we can just see that what analysis gave is well respected in this particular example. So you see that your estimate analysis shows that your error cannot exceed 0.0227. And in this particular case, since we can compute it explicitly, we saw that your actual error is well respecting your estimate. So this is the main aim of this example. In the last example, we have seen how to use Taylor theorem to approximate a nice function by a polynomial. By nice function, I mean a function which is differentiable as many times as we want its corresponding Taylor polynomial's degree. We will make this idea more precise by putting the same thing in a more general framework and in a little different way, which is mostly applicable in numerical analysis. Assume that we are given two real numbers, A and H. Say A is this and some H, for instance, H is a positive number, then we take A plus H. Similarly, if H is negative, we will be taking a point on the left of A. We are also given an integer n, which is going to be the degree of our Taylor polynomial. And once we are given all this, we assume that we are also given some n plus 1 set of numbers, which are generated using a function f and its derivatives. Once we are given all these inputs, now the question is, what is the value of f of a plus h, right? As I told you, we are given information about the function f at the point A, and we want the function value at the point A plus h. That is what we want, right? Well, we know only the function value at the point A and more information about the function at the point A only. Therefore, obviously, we cannot find exactly what will be the value of the function f at a plus h unless we know the function f explicit. Assume that we don't know the function explicitly, we only know all these details, but we don't know from where we have generated all these n plus 1 numbers. That is, f is not known to us. Then we cannot find exactly the value of f of a plus h. Now the question is, can I at least find approximately this value? If your question is this, then Taylor theorem is a suitable one for you to get this information. So what you can do is simply use these informations and build your Taylor polynomial, right? You can see that x is now a plus h. Therefore, x minus a is nothing but a plus h minus a, that is going to be h. Similarly, h square and so on. So this is precisely what we had defined as Taylor polynomial at the point a plus h. That is, this is nothing but Tn of a plus h. Often what we do is we generate this Taylor polynomial, and whatever value it gives, we will believe that that value is approximately equal to the value that we want. Okay, what is the base for this belief? Well, the base for this belief is the Taylor's theorem. The Taylor's theorem says that f of a plus h is nothing but Tn of a plus h plus a remainder, right? If your remainder term is going to be very small, then you can just forget it and take this value as approximately equal to the one which you want. Okay, but for all this, you need to make sure that your remainder term is going to be something very small that you can afford to neglect. Otherwise, this approximation will be bad. From our example, we intuitively see that as long as you stay very close to A, it means as long as your H is going to be very small, then you have seen, at least in an example graphically, that your approximation is going to be pretty good, right? Okay, this is a way we often use Taylor theorem in our course. That is why I put the same theorem in a little different form. That is, in the theorem we have defined it for f of x. Here we just defined it for f of a plus h. That is the only difference. There is nothing else. So as I told you, we will take our f of a plus h value as approximately equal to whatever your Taylor polynomial had given to you for a given h and a, right? This approximation will be good as long as h is very small. How small? That we don't know in general. It depends on the function, but intuitively or vaguely you can say that as long as h is very small, we believe that this value is going to be approximately equal to this value, right? At an approximation level, this is the best that we can tell. So as you know, why I have put approximately equal here is because there is no remainder term. If I would have had a remainder term here, I would have got an equal sign here, right? I would have got an equal sign if I would have had a remainder term also written. Put approximate symbol. You have to be careful while writing these expressions. Wherever the approximation is applicable, you have to put approximation symbol, not equal to symbol. So what is the remainder? The remainder term is given like this, right? Where this c is unknown. If that would have known to us, then we have an exact representation of this function, right? But that is not always possible. We do not know this c. The Taylor's theorem only says that there exists such c. It doesn't give us what that C is explicitly. So once you put the Taylor polynomial along with the remainder term, then you are allowed to put a equal sign. Otherwise, it should be only approximately equal sign. Okay, this you have to keep in mind always. And this term, as you know, is unknown, even though you know what is fn plus 1 as an expression you may be knowing often, but still you do not know this quantity because C is unknown. I am again and again emphasizing it. That is why we need to generally estimate this term in order to get an idea of how big the error could be. And as you know, C will lie between A and A plus H. That is, your A is here. You want to find the value of your function f at A plus H. So you agreed to take approximate value of f of A plus H, which was given by the Taylor's polynomial. Then the remainder term is given by this expression where C is somewhere in between A and A plus H. So C somewhere lies between A and A plus H. So as I told you, the remainder term involved in the approximation of f of x by the Taylor's polynomial is called the truncation error. That is this term, which in analysis we generally call it as remainder term, is here in numerical analysis course, we generally call it as truncation error.